Okay, so welcome back again. I hope everybody is alive and alert after a day in the sun. I tell you the rule of this presentation now. The rule is, if I see anybody falling asleep, you buy the beers. Okay? Okay. So we're going to talk a little bit about the properties of lime, renders, and mortars. And we're going to, I hope, once we finish this, we will have a break for as long as it takes for us to set up outside. And then we will do a little bit of a demonstration with the help of volunteers from over there and any others. Okay, historic uses of lime. Well, let's start off by making it very clear that lime as a building product, as a binder for structural elements of buildings, has been used for thousands of years. And testimony to its quality is the fact that we have historic structures dating back several thousand years where lime was actually used in the construction. The one thing I will say right from the beginning is that when I'm talking about lime and mortars, you must understand that a lime mortar, its purpose is to bind two blocks together, whatever those blocks might be. Mortar is not structural. Okay? The structural element comes, in this case, through the stones. So we have the Colosseum, which is about 1,000 years old. We have the Parthenon. Parts of it, oh, it's coming next, sorry. We have the Pantheon in Rome. The Pantheon in Rome, I have to look at the notes, I can't remember, was constructed around about 1120 AD, 120 AD. And it's more or less intact, and it's widely regarded as almost the perfect building in its structure, in its scale, and in the use of its materials. So the builders who constructed this, do we have the pointer? Really knew what they were doing. And this dome, for example, is constructed in what they call lime cement. Lime cement is not like modern cement. They're completely different. Okay, thank you. And the Pyramid of Giza, that's 6,000 years old. And those blocks, they're clearly piled together in a certain way that they become immediately structural. But they also used lime. And they used it with pozzolanic additives, which I'll come on to in a second. And the Parthenon. This part, clearly, is dry. It's not with mortar. The lower parts and much of the complex on the hill are with lime mortar. In all of these cases, the lime mix that was used included what is called a pozzolan. A pozzolan is an additive. It's added to improve what you might call the set of the mortar. It speeds up the chemical reaction. And typical pozzolans at the time were brick dust, brick particles, volcanic ash, anything that is going to speed up the chemical reaction. In the UK, lime-based materials were a part of construction of nearly every single historic building of this type, which is a structure with mortar, in the UK. And I told you yesterday, I guess, that there were about 500,000 protected buildings in the UK. Nearly every single one of them included lime-based materials. What has happened in the UK, particularly in recent years, is that there is a major movement back to using lime, to the old recipes, in order to restore these buildings. There was a period from the mid-1800s, from about 1850 till certainly till about 1960, 1970 even, where Portland cement was used. Are you familiar with the term Portland cement? Yeah? That is completely different from Roman cement. Yes, do you understand? Okay. And the two are completely different from the sort of mortars and renders we are going to be looking at. So, where does the lime come from?
Can I ask something?
Sure.
There are different mechanical properties?
Yes.
Okay.
Yes, and they have different reactions within the mortars.
Okay.
Yeah?
So it was dangerous to use in one part the Portland cement instead of
lime?
Yeah.
Yeah, it's disaster. It's not dangerous. It's absolute disaster. But I'll show you why as we go through. So, the types of stone that were used in lime production. The important thing is to remember that they have high calcium content. So, chalks have high calcium content. Limestones, high calcium, carboniferous. Different types of limestones, magnesium dolomite limestones, and then limestones with clay impurities. The limestones with clay impurities, I will go into in a bit more detail as we move through. They are the ones that tend to be used for hydraulic lime. The others are used for what we call non-hydraulic lime. Okay? If you remember the terms for the moment, I'll explain the difference between them as we go through. So, what is lime? Why do we use it? It's, as I told you, it's a substance that simply binds building together. The word lime basically means sticky, like a glue.
I'm going to get this, or do we have to?
Where's Mina? Are these all being copied for the students? Pardon? I don't know. Are the students getting these presentations? At the end of the workshop? Okay. Okay. So, lime is a substance which binds buildings together. It binds the main structural elements together. It's very versatile, and it's used for mortars, renders, plasters, and paints. For me, it might be a different terminology. So for me, a mortar is what goes between the stones when you're building walls. A render is what you put on the outside of the building to cover the structure for protection. A plaster is what you do on the inside and the ceilings. And for paints, there's a substance called lime wash, which we will come to at the very end of the presentation, which is like a paint, but a very, very, very liquid paint, which you put on as a sacrificial element. It protects, and it has to be repeated year after year after year. Okay. So the characteristics, it's stickiness. It provides adhesion between the materials. And if we're able to do a little bit of work outside, you'll see just how it, if it's put on correctly and it's compressed correctly, how it will hold, let's say, two stones together. Okay? Its workability is very, very important. Its plasticity. This means that when you mix it and when you work it, It's very, very easy to use. And it lasts in the way that cement does not. If we mix cement today, you have to use it today. If we mix lime mortar or lime render today, I can use it in a year's time, provided I protect it. Okay? It's very durable. You've seen it's clearly from the age of the buildings which are still standing, which have resisted over the years. And we come to this. If you remember anything at all about what I say tonight, remember that. Breathability. Lime allows a building to breathe. And we'll come into the details of what that means. But that is one of the most important characteristics of the use of lime in mortars and in renders. Okay? What it means in summary is that it allows moisture to travel through the walls, to come in, go out and stay out. It has a very soft texture, and traditionally older properties, particularly cottages, small houses, etc., they have a particular feel about them, they have a particular warmth about them through the use of this material. They have very low thermal conductivity. So when it's really hot out there, and you go into a house that has been constructed using lime, it's nice and cool inside, yeah? And during the winter, it's the opposite. It holds heat within the building. It allows for salt resistance and dispersal. That's something that affects many, many buildings, and particularly these days, buildings which are built using modern bricks. And the lime allows the dispersal of that to come out through the building. Maybe you've seen for yourself buildings with a white shadow, or like cotton wool on the facade of a building. That is the salts coming through. It has autogenous healing characteristics. Do you know what that means? No? It means that it heals itself. The ability to heal itself. It allows for small fractures. It distorts rather than collapses. And if you, let's say we have a wall where there's some ground movement, and there's, as a result of that, there's going to be a movement in the wall. If it's constructed using lime mortar, the building will move and find its own equilibrium because the mortar allows it to do it. If it's constructed with cement and you have a fracture here, that fracture will work its way down, right down to the bottom, and it'll collapse because cement does not have the capacity for elastic movement. Okay? It can serve as protection. It can be sacrificial, the lime washes, which we'll come to in the end. Now, the really important difference between lime and cement is that lime does not set. It doesn't become hard. It carbonates. It carbonates through the reaction of air in what we call air limes. So it actually, once you put the lime in a mortar between two stones, it's affected by the reaction of the air, and it carbonates. It doesn't set. Okay? You understand the distinction?
Not really. Can you say it again?
When let's take cement. When you use cement, you put it between two, let's say, two bricks. The cement goes hard very, very quickly. Yes? With lime, it doesn't. It carbonates. I'll show you the carbonation cycle in a minute. It does not set, it does not become solid like cement.
If you add water on it, it will dissolve?
No, no, you'll see. No, you're jumping ahead. Okay, no problem. There's two basic types of lime. Non-hydraulic lime. Sorry, I didn't see. No?
I think setting has to do with volume as well, because when it sets, it maintains its volume, but when it carbonates, it expels water. Something reasonable.
Not quite. Not quite. I've got a couple of slides which shows this process, so I'll explain it when we come to that, okay, if you don't mind. So, non-hydraulic lime is the lime that is affected by air. It carbonates. Hydraulic lime can be used with water, in water. So structures like this, like a lighthouse, the base of this at least, would be constructed in hydraulic lime. Non-hydraulic lime will not react underwater. It's no good. Okay? It has a different chemical content. Hydraulic lime has an extensive clay content, which contributes to the chemical reaction. Non-hydraulic lime has very, very little clay content.
And the hydraulic lime is not breathable?
It is to a point, but it's not as breathable as non-hydraulic lime. Yeah? So, this is basically what non-hydraulic lime looks like as what we call a putty, a paste. It's like a big ice cream or a big yogurt, but don't eat it because you'll die, and don't put your finger in it because it'll burn. Okay? It's made from the purer limestones, and it carbonates only. It's called fat or lean. Those are, if you see those terms with reference to lime, it means that it's a non-hydraulic lime. It's stored as a putty. This is the putty, and we have some outside, so you will actually see what it looks like. It improves with age. The longer you can keep it, the better it is. They say that you shouldn't use lime putty if it's less than 1 year old. In reality, that doesn't happen because a lot of these putties are now produced commercially, and they're delivered to site in bags, or they're delivered to site in a bucket like this, and they're often no more than 3 months old. It doesn't mean you can't use them, but the quality will not be as good as if it's been kept for a year or more. The older, the better.
The older, the better.
Yeah.
If it's more than 2 years, then it has some problems.
No. I'll quote my friend here. 7 years is the rule, I was told today. It's perfectly okay. If it's 10 years old, it's perfectly okay. Okay, it's often stored in pits, and the pits are covered with a sack, a hessian, and kept wet, and that way the air doesn't get to it, so it doesn't start to carbonate. So, let's have a look at hydraulic lime. Hydraulic lime comes in a powder. And this is part of the production process. You'll see in a minute how this lime is actually made by burning it in kilns. And the production process is such that hydraulic lime ends up as a powder. It has reactive impurities, and mostly related to clay. And it's those impurities that give it a chemical quality that gives chemical reactions which are completely different from non-hydraulic lime. It includes illuminates as well as, depending on where you use it, it will have a chemical set combined with a carbonation. But the principal thing that it will have is a chemical set. Their hydraulic lime comes in powder, it comes in bags. There are classifications under EU standards. You will see written on the bag NHL, NHL 2. 2 is the weakest of the hydraulic limes, 3.5, and then 5 is the strongest, is the hardest. And I'll show you why in, not the next slide, but one or two later. It gains strength over time. So it gets harder and harder, but very, very quickly. Anything below NHL2 is not really recommended in building construction. But there are instances where you might be working with a non-hydraulic lime, which you have extracted directly from the kiln, and there might be impurities within that which are to do with the burning process. Those impurities will change it from non-hydraulic to semi-hydraulic, to almost hydraulic. And so it's very, very important to understand these distinctions and the ways in which they should be used in the buildings. You need to be clear what impurities there are. Original samples for lab analysis. It's, if you're doing a restoration on the building and you want to get it as close to the original as possible, it's normal to take some samples and send them to the laboratory. Those will be broken down into their constituent parts, and they'll guide you as to what sort of lime and what sort of sand and what sort of additives. Yeah? Am I talking too quick? Are you okay? Yeah? There is a third type, which is hydrated lime. And this is basically lime powder. When it's lime putty, which has been hydrated, the water has been taken out of it. This is the sort of thing you get in the building suppliers. If you go and ask for hydrated lime, you get a bag of white powder. And it can actually be used in that form. It can be used and mixed with a sand, with an aggregate. But strangely enough, it can be added to water to if you add water to it, you can produce you can return it back to a lime putty. You can bring it back to a paste, and it can be used after 24 hours. It is not as good as lime putty. That's pretty clear, and it's not as strong, but it's actually better. It's purer and gives a better color for lime wash. If you want something really white, it's better to use the powder than it is to use the putty. And you can mix it. You can mix it with aggregates. So let's look at the cementation index of lime. These fat limes, these non-hydraulic limes, have very, very, very little clay. 2% on average. Feebly hydraulic lime, which is the NHL2, has around 8% of clay. Moderately hydraulic lime which is NHL 3.5, has around 15% of clay. And eminently hydraulic lime has around 25%. That is NHL 5. NHL 5 is, sorry?
Oh, when you're saying clay, you mean the clay they put in the kiln and burn with it?
No, 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 they don't put clay in the kiln.
You mean
The clay in the stone,
Oh, in the stone?
in the original stone.
Yeah. It's burned with the stone.
The stone is burnt. Non-hydraulic lime is burnt at a different temperature from hydraulic lime. And that's because of this difference in the clay content. So the natural stone has elements of clay within it. Yeah? This NHL 5 is very, very, very hard.
By volume or by weight?
Sorry, by?
By volume, the ratios.
Yeah, by volume. Yeah. This NHL 5, I have to tell you to be very careful. If you use it in rendering, if you use it for covering the external walls. I learned the hard way because I made a mistake and used it. And we rendered an external wall and left it for a couple of days before we wanted to put the next coat on. And I realized that it was setting too quickly. It was getting hard far, far too quickly. And so we made a decision to accept, okay, you messed up, let's start again. So we tried to take it off. And it is so hard that if your substructure, let's say a normal clay brick, is soft, it takes the face of the brick with it. So you end up destroying the building that you're trying to repair. And we had to start completely from the beginning.
Can you repeat what was your mistake? What did you do wrong? What did you use wrong?
We used NHL 5, which is this, eminently hydraulic lime, on the exterior wall of a building. Not as a mortar between bricks, but on the face of the building. Yeah? And it hardened very quickly. It was clear that the set rate was too rapid, so we decided to take it off. And within about 2 days, it had set so hard that when we took it off, it took away the face of the bricks because the bricks were very soft. So we had to redo it.
You had to remove it because of what?
Pardon?
Why did you decide? Because it was setting too far?
Yes, and it was clear that it was a bad choice.
Why is it bad that it sets too fast?
It was stronger than the painting material itself.
Yes, the actual structure was in very, very soft clay bricks. It was an old structure from about 1750, and it was clear that if we left it on, and there were going to be any problems with it, let's say it fractured in the future, and rain got in behind it, it was going to destroy the bricks anyway. So we decided to accept that we made a mistake and did it again. Oh, we're stuck on this point. Yeah?
But isn't it some kind of protecting although it's, let me find the word, although it was a render, wasn't it kind of protective for the brick? Why would the water go behind the brick?
Because we felt that there was a danger that because it was setting so quickly, any water within it was being absorbed into the bricks. And we were afraid that eventually you would get small fissures, small fractures. And if water got into that and got behind, there was going to be a problem. Yeah? Okay, what's next?
One more question about this.
Yeah?
If it were, let's say, for a lighthouse, it would have been better, this type of method?
For a lighthouse, yes.
It was looking for lighthouse, and you decided to use it on the country base?
You can, well, in Romania, you can only get, if you're using hydraulic lime, you can only get it from certain sources, and it's often an Italian lime that's imported. Sometimes they, even if you specify, if you say, I want NHL2, if they don't have it, they don't care, they'll send you NHL5 because they want to make a sale. And we were in a position, we were actually running a school, and we needed to do the work for demonstration purposes. It was a bad decision, and that was it.
Can I ask one question? Is hydraulic lime also breathable?
Yes.
Okay. So if water got into the structure, wouldn't it just go out there?
No, not in the same form as, not in the way that it can come out with non-hydraulic lime. It gets trapped as if it were cement. Everything that was on that last slide we've already covered in what you've asked, so there's no point in going through it. So let's have a look at this, this spectrum. The top heading says impurity and strength. If we start with lime putty, which is non-hydraulic lime, it has very few impurities. But very little strength, yeah. Lime powder, which is hydraulic, is somewhere in the middle. Natural cements are at the top of the strength chart, and they get stronger as they get older. The opposite is the case with permeability and breathability. So natural cements, hydraulic limes, are significantly less breathable. They start at this end of the spectrum than lime putties, which are almost completely breathable. Yeah? Yeah?
This natural cement is a lime mix as well, no?
No, it's, yes, it's just this, yeah, yeah. But it is very, it has 45% clay. So, okay, so let's see how this actually impacts on buildings. Let's look at the difference between a basic modern construction and an historic construction, and how this element of breathability actually works. A modern construction is often built of two walls with a cavity in between, and frequently within the cavity there are systems that collect the water, take it down and out. They're specifically designed to stop rain coming in. So the rain will run down the building. Within the structure, you have what's called interstitial condensation. And there is in this building now. We have significantly added to it by our presence, because we're all hot and sweaty and the air is wet and humid, and the water is going into the walls. That water can travel through to the first wall, but not the second, and it comes down the cavity and out. On a solid wall of porous materials, which is let's say clay brick, or let's say stone. This is the old construction. What happens is that the rain will come into the structure, but because everything is porous, including the external render, the water can evaporate. Yeah? And the interstitial condensation, which goes in, this is the water vapor, it can find its way back out again. Okay? What would happen? What would happen in a situation like this? On this external wall, if I take off all the render and I decide to repair it using cement, what will happen? Yeah. Exactly. What would happen is that the water would come to that point, it is nowhere to go, so it come back in again. And that's why you often see walls in older houses where you get particularly damp marks at the top and rising damp at the bottom in combination with the water coming up from the ground and the water being trapped within the wall because it can't go out. All it can do is come back in again. Okay.
If it is insulated from all sides, how will the water penetrate the wall?
Sorry?
If it is insulated from all sides, including the foundation, how will the...
Insulated with what? Insulated with what? These walls are often very thick, solid structures, and that solidity reduces the need for insulation. I can tell you that in Romania, on the older houses now, let's say houses from the 19th century, two things are happening, two terrible things. One is that they're changing all the windows, taking out all the wooden windows and putting in new PVC windows. The first thing that happens is that the interior of the house gets incredible condensation. So they decide to insulate. So on the outside wall, they put polystyrene blocks. And what happens? The water comes back in again, and they get even more condensation. So I would never recommend put in insulation in a situation like that.
Yes, but this happens only in historic buildings, right? What will happen for a modern construction? Why should somebody use lime instead of cement?
With a modern construction, it's completely different. It's a different building system. So the insulation is an additive if you want insulation. It doesn't affect the movement.
Yeah, but why would you recommend to somebody to use lime in modern construction?
I would only recommend them to use lime in modern construction if they're using traditional building materials. If they're using cement blocks, I wouldn't speak to them first of all, so I wouldn't be able to recommend them anything. Okay.
Isn't it true that, it isn't really proved how long cement will actually last, but it may actually not be lasting much more than 100 years?
Well, that is correct. Well, that's correct. And it depends on how it's used, where it's used within the building, whether it's reinforced cement or whatever. So, breathability and sacrificial use. Sacrificial mortars and renders should be softer than the masonry which they protect. That's a rule. Okay. Sacrificial mortars and renders should be softer than the masonry they protect. So let's say we have stone blocks here, here, and here. The mortar that goes between them is only there to stick them together, nothing else. I told you it's not structural. But that mortar should be softer than the stone. That means that when water enters the stone, water will always find the easiest way out. The easiest way out is partially, thank you, partially through evaporation here, but also it will go down into the mortar. So the mortar has to be softer to allow the water to get out. Yes? You understand the principle? If you're repairing a building which is the same stone, and you use a cement mortar and not a lime mortar, your cement mortar is acting like a plug. It's like a block. And the cement mortar is actually stronger than the stone. What happens? The water comes down. It can't get through the cement, so it goes around it, and you get erosion at these points. And you get the stone becoming eroded on the outside, and the mortar will actually project. I'll show you.
Can I ask something?
This, yeah.
If the cement is on the foundations, it's the same problem, or we don't care it because it's underground?
No, it's not the same problem. No. But the most important thing in that sort of situation would be to ensure that there's proper drainage all around the building. So you would normally dig a drainage channel about 300 mil deep. You would put in a perforated pipe, and you would cover it in stone. Yeah. So this is what happens. Cement, plastic paints trap moisture and do not breathe. So this is a stone where repointing was done using cement. The water couldn't get out through the cement, so it came out through the stone. And the face of the stone is lost. Same here. I'm sure you've all seen examples of this at some stage or other. What's the next one? Oh, yeah. And here, for example, this is a wall where the top part collapsed, but what it revealed was that the wall itself had cement mortar. And when the rain came, the rain couldn't get anywhere near the cement, so it found its way into the bricks. And when you get a winter, the bricks are softer, the bricks will retain the moisture, the frosts will expand the bricks and blow off the face of the brick.
But if that gets into the mortar, if you have limestone, lime mortar, then that wouldn't happen to the center of the wall.
No, no, it wouldn't happen.
Why wouldn't the frost crack?
Well, in that situation, this is different because it's a damaged wall and the top came off. If it's protected, and the
I mean, like in the same case, if
yes.
if the top broke,
yeah,
and it revealed the lime underneath,
yeah,
then that wouldn't break the wall from the inside.
No. The mortar would crumble first because it's softer than the brick, and it's easier to repair the mortar. Okay, some other benefits of using lime. Oh, it's lovely and cold. Structural flexibility. No expansion joints. You can build a wall as long as you like, and you don't have to put expansion joints in the way that you do in modern structures when you're using cement. It's salt resistant. I told you how it works with the salt. It's removable and allows the reuse of masonry. If you try and, if you find a wall or a building, let's say 3 sides have collapsed over many years, and you want to take down the 4th wall, if it's constructed using lime, you can take it down easily. If it's constructed using cement, as soon as you try, you'll smash all the bricks. They will all break. Sustainability is an issue these days. It seems to be that you always have to justify the CO2 reactions. But what it does do is allow recycling. So you can reuse it. And compatibility is very important. Lime and lime additives is compatible with stone and with clay, provided that that the lime mortar is softer than the base material. Okay? So, how does all this work? I want to show you some lime kilns now in a minute. But first of all, you need to understand the lime cycle. Let's do the, it's easier on the next one. Yeah, that's better. What we start off with is chalk, limestone. It's calcium carbonate. Through the lime burning, that loses the CO2 content of the stone, and when the lime burning is finished, we end up with quicklime, which is calcium oxide. That calcium oxide as quicklime is then put into a pit, and water is added. And the effect of the water, the effect of that is that the quicklime sucks up the water and expands and becomes a putty. And that process is called lime slaking. We then get to the final process is the production of calcium hydroxide, which is the lime putty. And if you want to take the water out of that again, you get the powder, which is the dry hydrate. You then mix it with the aggregates, and you use it in your wall. And it absorbs moisture from the air, and it gradually, through the chemical process, carbonates and changes back to where it began. So it carbonates in such a way that it's always tending towards becoming calcium carbonate again. That's called the lime cycle. Okay? Understand? No? Yeah? This is basically how it happens with a kiln. You fire the kiln from the bottom. The limestone is fed in from the top. You get layers of timber, layers of stone, layers of timber, layers of stone, all the way up through. I'll show you some actual slides in a minute. And through this burning process, we change from the original material through to the quicklime. And when it comes out of the kiln at this point, that's the quicklime. These are little blocks which you're going to see. You know, we needn't do the quarry. You know what a quarry looks like from today. These are just examples of lime kilns from previous period. This is a lime kiln near me in Romania. It's built into a hillside. The firing hole is here. The stone was put in from the top, and then a clay cap was put over the stone to hold the heat. So it looks a clay cap, just to keep the heat in. So that's what it looks like. You put in a range of different size blocks of stone, and as the fire burns, they burn down through. It's clear. Okay. This is last year. I was working in Albania, in Korça, and we were lucky enough to find a kiln that was actually being fired while we were working. So this is what it looked like. This is what it was like on top. And the fire was so intense, it was coming up through. You can just about see a line, can you? There. Yeah? A black line here. That was the height of the stone when it was first put in. And then it drops as the burning process continues. And the whole thing is fired from underneath. In this process, for non-hydraulic lime, you have to get the fire up to 900 degrees C. And that usually burns for about 3 to 4 days, depending on the size of the kiln. If you're using stone with, which is going to give you a hydraulic lime, you have to get the kiln up to at least 1,400 degrees. So it's a different rate of burning, and it's a different process in the end. So what does all this produce? The kiln you've just seen, it uses 60 to 70 cubic meters of wood on one firing to keep it going. 50 tons of limestone produces 25 tons of quicklime. So whatever, this is an average, whatever stone you put in, you get half of the amount back. 2.8 kilograms of lime putty can be, let's say 3 kilograms of lime putty can be produced from 1 kilogram of quicklime. So these are average figures. Yeah?
How can you reach up to 1,400 degrees just by burning wood?
Quite easily, as it happens. Yeah. Yes, of course it's possible. Yeah. It might be a slightly longer. You need a good hardwood that's going to burn well and retain heat. Yes. Yes. So, where are we?
Aren't there more efficient kilns for making quicklime, or generally made this way?
Are there more what?
Are there more efficient?
Yes, sorry, I didn't hear you. Yes, of course, but these are, there are commercial kilns these days which burn 24/24, and they produce this on a commercial business basis. But what I'm showing you is the traditional way of doing it. It's still done like this in Romania, particularly in the mountain areas, where 3 or 4 villages will share one lime kiln. So, this is the slaking process. You put the quicklime into a container, a basin, or whatever. You add water, and there'll be an immediate reaction. It immediately causes heat, and it's very dangerous. If we do it tonight, you have to make sure you stand well back, because it can really, really burn. The lime putty is starting to form here in the slaking process, and this is what you would get, a slaking pit. So it's a huge pit basin where the lime, the quicklime is put in. It's covered in water, and it will absorb all of that water to become this. This is actually still working. You can see at the top it started to solidify, but it's very, very soft and not ready at the bottom. And this is something which the craftsmen who are doing this would be able to advise you on. In some cases, you get lots of impurities. You see all the little black bits? That's the impurities from the kiln. That doesn't mean it's a bad lime. It simply means that when you use it, it will change the chemical reaction with, within the lime, and it will make it slightly harder. It'll make it semi-hydraulic. And in some cases, that's actually very good and what's needed. Okay, I think we need to move pretty quick because we've got lots of slides. We do, yeah. 1941, 7, 8, yeah. Okay, the standard mix is 3 parts aggregate to 1 part lime. It's very, very simple. That will vary depending on what work you are doing, depending on the type of aggregate that you're using, depending whether you're going to add pozzolans. Richer mixes can be increased towards 2 points aggregate to 1 part lime. But you need to remember, particularly if you're doing render and you're doing face work, the richer the mix, the more likely that there will be shrinkage cracks. Quite often the final mix might be 1-to-1. It might be 1 part pure lime putty to 1 part sand. But the sand will be very, very, very fine, sieved sand, like a sea sand. And you have to be very, very wary under what conditions you use that. Otherwise, it will shrink and it will crack too quickly. The age of the lime will definitely affect the mix ratio. I think you can only judge that when you're making it by being used to the mixing process and to be able to see a lime putty and know whether it's a good one, a bad one, too much water in it, or whatever. One of the things that is very, very important when you're using non-hydraulic lime, when you mix it with an aggregate, you do not add water. Because if you add too much water, it weakens the mix, and the water will be absorbed into the building, and the render will crack very, very quickly. So you do not add water. Analysis of existing render. Obviously, if you're repairing a building and you want to match in, then you should do some sort of analysis. Effects of adding cement. There was a period in the 1990s when English Heritage were recommending adding 1 part cement to 2 parts lime to 9 parts aggregate, sand. That ratio is still 3 to 1. But what they were suggesting was that in certain positions on a building, let's say at the lower part, where there's danger of water penetration, danger of rising damp, and up on the very top, let's say on the chimneys, that where there is also more than normal weathering, they were recommending this sort of mix on the basis that they felt that the addition of cement would firstly move the chemical set on a little bit, and they would get earlier protection. What actually happened was the exact opposite, because the cement and the lime have completely different chemical reactions, and the lime was basically frustrating the carbonation of the cement was frustrating the carbonation of the lime. There's a report which English Heritage did. It's called the Smeaton Report, which explains this in extreme detail with all the chemical analysis, etc., within that report. So, never, sorry? Smeaton. Smeaton. S-M-E-A-T-O-N. It's not good practice, no. No. The other thing I should have said about the aggregate when you're mixing, when you're making the initial mix, it's very, very important that the aggregate is completely covered in the lime. So if you use angular sand, angular aggregate, then it's pretty clear because of the angles. It's going to be far easier to make sure that the lime is covering everything. If you use rounded aggregate, it's much more difficult to ensure that. So it's very, very important. And the normal type of aggregate would range in size from 0 to 3 millimeters, depending on where you're going to use it in the building. But the average is 0 to 3 millimeters. It's very, very common when you're rendering to do 3-coat work. But before you do any work, you have to mix. You have to mix the mortar, the render. And some of you are going to be doing that shortly under my guidance, so that I don't have to do it. And there is a test to see whether it's good or not. When you mix it, whether you do it in a mixer or whether you're mixing it by hand, you have to get it to a certain consistency for it to work well. The trick is, let's say we have a wheelbarrow in front of us, which is full of a brand new mortar which we've just mixed. The trick is to get your trowel, put it in, to take a sample out, turn your trowel over. If it falls off, it's no good. If it sticks for a few seconds, it's good. Okay? It's a very, very simple trick. All the builders use it. So the backing coat, the very first coat you put on, would be 3 to 1. In some renders, you can gauge that with hair to help it bind. The thickness is the important thing. It should not be more than 12 mil. The first coat should not be more than 12 mil. The second coat, if anything, should be less, so it should be 10 to 12. But it's applied only after proper drying of the backing coat. So one of the reasons that builders do not like to use this process is it costs them time. It takes, depending on weather conditions, it might take 2 days, 3 days, 4 days. It might take a week for the first coat to get to a point where you can put on the second coat. But what is important is that that first coat has to dry. But before you put the second coat on, you have to spray it with water. Otherwise, when you put the second coat on, it will suck all the water from that second coat, and the whole lot will fall off. Okay? The finishing coat can be 1 to 1, 2 to 1, 3 to 1. It depends on the conditions. It depends on what you're actually working on. The mix will affect the drying and workability, and as I told you, you have to use very, very fine sand. And final protective finish, if you want it, can be a lime wash.
Can you explain about the hair on the first?
Oh, sorry. The backing coat, the very first coat that you put onto the wall, you can gauge that with hair. You can put hair into the mix, and it helps in binding the render together. It's usually animal hair, goat hair, cow hair, horse hair mostly in the UK. There's those amongst you who have got beautiful hair, and you can use human hair. Yes. There was a period when I know.
How do you know when one layer is ready, dry, to put the next one?
You touch it, you feel it.
And the surface is...
It's not completely dry. When you've put the first coat on, even if you see it cracking, it doesn't matter, because as long as it's still flexible. The trick is to run your thumb down the crack and pull it back together again. If if when you do that, the mortar or render crumbles, it's too dry, and you have to re-wet it. Okay? Okay. Oh, here we go. We've already mentioned this. There you are, the Smeaton project. What happens is that it speeds up the early set. Okay, but that's not what you were looking for. But it adversely affects breathability and long-term durability. So, as I've said, it is not good practice to mix cement with lime. So, pozzolanic additives. There are many types of pozzolanic additives. One of the most common for me is brick dust, or crushed brick. Not dust, but crushed into little particles so that it looks like a sand, and it's all angular. When what happens with that is it improves the strength of the mortar, and it speeds up the process a little bit. If you're using brick dust or crushed brick, you shouldn't really use more than 8 to 10%, because it'll make the mortar too hard, and the reaction between the lime and the brick will be too excessive. The other thing about using crushed brick, let's say we're going to use crushed brick in a mortar between two stones. When it rains, you've seen the diagram, the water goes into the stone, it comes back out through the mortar. If you're using very, very small particles of brick, the water will go into that brick, it'll be absorbed by the brick, and it'll be released much more slowly. So the breathability is actually improved. Okay? This again is an average, hair for renders, cut to 35 to 90 millimeter lengths. This is not a Bible, this is not the only way of doing it, but it's an average. And the mix is approximately 0.5 kilograms of hair to 100 liters of mortar. Okay? So that basically works out at 2 good handfuls of hair to 1 wheelbarrow, and you tease it in. It's called teasing it in. You don't just throw it in. You put some in, mix it, throw some, put some more in, mix it. Okay? Okay. Okay. Crushed brick and ash pozzolan. This is actually a repair within a stone wall. The stone wall dates from around about 1200. And part of it, one of the stones had collapsed. This is an alternative repair. We could have put a new stone in there. It would have looked like a new stone, okay. But we decided to follow the principles of the SPAB, the Society for the Protection of Ancient Buildings. And one of their principles is that if you do a repair, it has to be what they call an honest repair. So you should see your intervention. And so this is one of the systems that they recommend or suggest. It's basically clay tiles held together with a mortar. But within the mortar, there's crushed brick and ash, fire ash. Can you see all the little spots, all the little black bits? So that's gauged into the mortar at the ratio I told you, 8 to 10%. And so this is what they call an honest repair. But that's what a mortar looks like if it has the crushed brick, etc. Sorry, I didn't hear.
Is there like a, you said that the SPAB
Yeah?
is suggesting the visible repair.
Yes.
Is there like a catalog for this?
Yes.
Like what we can do?
Yes. At the end of the presentation, there's a bibliography. and within that are all the WW addresses, including SPAB. Okay? So, you've seen this building yesterday. This is back to Banffy Castle. Because it had so many problems, it's always easy to use it in talks like this, because it represents everything that we are talking about. So we're looking at a tower here from 1650. The structure of the tower is the base. The main structure is stone. In some cases, brick was added in to level the courses, and then a backing coat was put on, and it moved through, and actually 3 layers, to a top coat, and the top coat was then rendered. In the 1920s, that top coat was changed. All of these little holes are hammer holes into the original render, so that when they put on